Hi there. I have to adjust my voice. I would like to introduce a little bit of the context behind how these things are made. We heard a lot about making stuff from Google to Yangfeng to Dan's presentation earlier, and these digital twins can be very helpful when you put in the context of making stuff that actually can have predictive properties. So how can we do this? Connecting things, as Patrick said earlier, is a concept. It's a concept that involves multiple steps. In our case here, we try to focus on cyberphysical systems because we try to bring together, integrate together concepts and sensors and devices that seamlessly don't work unless you put the interface together. So we put a digital engineering ecosystem that involves the design, the testing, the validation, the packaging, the scaling of those systems in the context also of making a digital replica. So imagine we have legacy systems like this power plant here that exists for 130 years, but we can take that knowledge and put in the design phase now of making a new power system where at the same time we're making the physical asset, we construct its digital replica. What would that be? Well, we have to enable some key functions, real-time monitoring, data, simulations, and AI that can work with different components. And of course, we want to achieve some functions, such as diagnostics and prognostics. So at Rowan, as in other places in this country and the world, we try to bring this digital engineering ecosystem together to make some applications happen. And how do digital twins come together? We heard the term virtual twins. We heard the term virtualization quite a bit. But in our case, as Dan at Digital Twin Consortium defined, we try to essentially focus on two important aspects. Digital twins of something have to have a virtual environment. We understand that. But virtual environment alone won't give you the two functions that you actually care for. Number one, synchronicity, meaning can we time-wise make the systems work between physical and digital realms so they're synchronous in some level of synchronicity. And with the level of synchronicity, we want to have actually a level of fidelity, meaning is a simulation of the wind turbine you see there an accurate depiction of the current state? And if it becomes the accurate depiction of the current state, can actually produce a future state. And if the future state is reliable, can it train my model to predict that fault whenever this fault appears? So Dan, again, leads an effort that actually involves multiple applications. So domain experts like myself that focus on materials, structures, and manufacturing can talk to domain experts in medicine, domain experts in energy infrastructure, and understand the tools and architectures that actually are common between all those digital twin development. Are we the only ones thinking about this? Are we the only ones that actually think of how we can do this digital twinning operations? Fortunately, no. Here in the US, there's a publication you can actually look up, the 5000.97, that actually defines a little bit of a structure of how this digital twin development can happen. As you can see in the chart here, we're talking about a synthesis. Patrick talked about metamorphosis before. Indeed, is changing the way we think of engineering. So what if at the time you build a system, you think of hardware, software, network, tools, and people at the same time you actually design the system? So that inspection plan, that maintenance strategy, that repair strategy, and that overhauling strategy are integral to the way you design the system. So going from a digital thread of connecting this information to a digital artifact in which we can virtualize an asset and bring it in, to a virtual model that can actually take the digital artifact now and put it into some sort of function to create now a functional digital twin. Can you imagine what this can do? Well, in practical terms, we have to make stuff. And to make stuff, you need new technologies. So here I can present you what we can do to make perhaps the most abundant of materials out there. So if I ask you to take a guess, which materials used the most to build the physical world, can you give me some materials? I will claim that metals is one of them. So what you see in these videos is examples of how, in this world, we can make large structures. When I say large structures, extremely big. We can make meters over meters of metallic structures that can be anything. They can be part of a rocket engine. They can be part of a vessel. They can be part of a construction site. And the technologies to make them are advancing rapidly. As you can see in these videos, we can make robotic arms that actually can deposit matter at the same time they actually form the shape of our design. We have lasers, like you see in the video on the right, I collaborate with DMG Mori, that can literally take that particle of matter and fuse it, sinter it, to the point of making something which is not only dimensionally accurate, but can inscribe information never possible to be made before. But that's a very scientific process. To actually understand the way we can change the way we make materials, we have to understand how matter interacts with lasers. And that's what Patrick called earlier today a science problem. But if we actually understand the way we can make that feedstock material, and we can fuse it, we can sinter it with the help of thermal energy, like you see in this picture on the right, what can we achieve? Well, hopefully, by making a part, we can make the desired outcome of operations of making something. We can make a device, a component, a part. But down in the science of things, we can actually make the material itself. So what if, like we heard about proteins this morning, what if at the same time you make the part, you can actually customize the way you make the material? So what you see in this chart here, sorry about the scientific jargon, is growth on the x-axis, temperature gradient on the y-axis. What if I control the temperature by which I make something and the rate in which I grow this material at the microstructure level to make a material that is unique to the operation I'm making? And what if I can collect data so that those intricate patterns you see on the right, the cellular, dendritic, and eco-EAX dendritic, are customizable, tailorable to make the properties I need on a Tuesday, on a Wednesday, on part X or part Y. This is the future of making anything, and the idea here is to try to put the tools together to understand this. Why do we need to understand this? Yang Feng talked earlier at the company about predicting performance. This is the value where simulation and engineering comes together. On the left side, you see a graph that engineers like myself are tortured on a daily basis. How long can my part last? How long can my implant last? When should I do repair? On the y-axis, on the vertical axis, you see how much load I can put on something else. So the problem with the way we make stuff now is that there's a tremendous scatter on the properties by which we actually can achieve after we make something. Not only that, if you go to the pictures on the right, we make stuff that actually, at the time that we make them, they have defects. Those are residual stresses, thermal fields, cracks, pores that are made while we make the part itself. So how can Dassault Systems, how can the engineering community help solve this problem? I put this timeline there between left and right in terms of one critical characteristic of models. We call it the opacity. How direct a simulation can be. Starting from the left to the right, you see different examples of simulation strategies, like reduced order models, physics-informed machine learning, and anything in between. So we have tools out there. Dassault Systèmes has a great variety of them. The question is, can we use them effectively to actually understand what is that we can get from these models to inform physics, to inform design, and ultimately perform some function? You can't escape equations. As Patrick and others mentioned, this is a science problem. When we try to actually play with matter and transform it from one state to the other, we have to worry about structural stuff. We have to worry about thermal effects. We have to worry about fluid structure interactions. And ultimately, you have to worry about the means by which we actually reduce temperature, heat on that particular part. So the simulations on the right didn't play. The simulations on the right were showing what is possible to be done. Unfortunately, the videos don't play, but what you get in the picture here is at the time we make a part, we can collect a ton of information. Information that comes from the part itself, such as temperature, such as internal things that can be seen in terms of defects, and imaging can help us quite a bit. So if I have physical information about the process, and I can combine this now with extremely accurate, fidelity-wise appropriate simulations that actually can emulate the process to create a digital foundry by which every time I make something, I have a digital replica of it. The question becomes, what can I achieve more? What you can achieve more is understanding what happens at the fundamental level of interaction. And why we care about this. We care about this because those machines are complex systems that actually can portray things in the way that we cannot understand sometimes. So interpreting results that are at the level of interaction is a fundamental way for us to go back and do design in a more effective manner. The simulations don't play, but what you see on the left is the way the machine executes the path of making something. If you can actually understand this path and the material that actually goes in this particular laser integration, you can actually tune the machine to achieve something that previously wasn't possible because you didn't know how to program the machine itself. So we can actually understand how the machine interacts with the material and how the material actually gets transformed to a part. It opens the way to digitally connect this information now and try to optimize it. Again, the videos don't play here, but simulations provided by Dassault can actually give you a lot of different information sources that you want to combine to get a clear picture. You can get thermal histories, heat flux, displacement histories, and stress histories to come all together now to complete what you want to have every time you make something. Let's call it the digital pedigree or the DNA of making anything. If this DNA now can be used with new machines, machines that perhaps you heard that companies are using already to do something, then that's interesting. Well, what you see here on the left is the first machine built here in the US that actually is what we call an IoT interface. Why IoT interface? This is not just a machine that shines laser and is able to zap this energy on powder and make the powder a solid part. It's a machine that actually provides you an interface that you can actually collect data as you make this. How much data? Terabytes. Every part, as small as a couple of inches, will produce a trove of data you have to understand, analyze, visualize, and learn from it in order for you to do something more. How can we do this? Well, we heard about AMD and companies like Dell that invest technologies themselves try to bring supercomputing power at the edge. That's what we have here. We built computing environments where we can stream data directly from machines to understand how we can process information in real time. This is Pythia, a computational cluster next to a single 3D printing device that is able to use thousands of CPU cores, hundreds of GPU cores, with the whole purpose to do real-time AI. Not AI on databases, not AI on stored data. AI on data that keeps streamed as you operate. We're talking about latencies and throughputs. Latencies of milliseconds or less. Throughputs of gigabit a second or more. So how can I invest on a computing infrastructure that could be surrogate and actually corroborating with a physical process in manufacturing? The key to all this is one. Can you guess? Data. Data comes to us. Data can be useful, but data alone is not the answer. For each piece of datum, you have other pieces of metadata that you have to organize them. So an engineer today is much more of a data scientist than ever before, because each system that we're using in a cyberphysical setting is producing information about the process, information about the material, information about the transformation that happens while thermal effects, heat effects in general, stress effects come together. So what if this data is structured in a way that actually can go all the way to the source code where the machine is using? In the Dassault system ecosystem of software, we have the ability to link now this information into a structure that we can go all the way down to the toolpath, to that number that we have to plug into the machine to get that parameter optimized to give us the result we need. And the question now begins, as Dan mentioned and others, can AI help us? What do you think? Can AI help us? It can. In what sense? We put a notional schematic here in terms of how a single LLM, call it an agent, can actually orchestrate a number of functions within this manufacturing ecosystem. Patrick, you mentioned about this interface between AI and manufacturing. A database is created every time we operate a single device or a factory that has multiple devices. And we have to do certain functions, such as train models, log this information, or link sensor data to the process by which we actually collected this database information. That's the orange boxes. But we also have to deploy APIs, interfaces, by which we have to, for instance, control something, or things that have to do in terms of code generation to do something else. In some cases, like a robotic device, we have to actuate a system. In some other cases, we have to communicate to a network, a cloud, to store information or inform a manager. And in some cases, we have to interrupt or do a prompt query to actually allow us to do something different than what we started with because something went wrong. Well, how can you do this? Well, there's protocols out there that you can actually take advantage of to structure the information that comes in. So what you see here in this diagram is an open standard called interconnect that helps you to link information down to the granular level of where it came from. On the left, you see 3 systems in blue that produce data: an acoustic emission data acquisition system, a 3D printer, and cameras. You communicate this information out to this blue big box in the middle that has 2 components: an adapter that is able to read this data, and an agent that actually talks to adapter automatically and structures the data in a way that can communicate now through a connection somewhere else. If you don't have this interface, the data that comes in is what we call raw. And raw data cannot be used unless you have some structure around this. So talking about usage. Once you do this infrastructure, you create something called, for instance, an XML structure. This is useful. It has all the raw information in a database frame that actually you can query and you can parse. But if you want to run AI and you use a parsable and queryable version of the XML, you cannot create something called an SQL database, which is a parsed version of the XML, that has information about your process, such as your timestamp, your temperature, your pressure, but also has a label that an agent or an AI model produced, with 0 being no defect and 1 being defect detected. So you have augmented now what came physically and digitally to you through the system with something that AI has been able to nuance so it can take it a step further. And what's a step further? It's a picture like this, where essentially you see an instantiation where we have a physical system working and is able to 3D print. And at the same time the physical system is working, a digital system is mimicking in real time what the physical system does, 100%. So we captured 2 things in this picture. We captured the past and the present. And what's the ultimate goal of an engineering cyberphysical system? Capture the future. I call it the T+N project. If we can actually understand what's going to happen at time t plus 1 second forward, we might actually catch the defect from forming. So the system here is able to integrate in a virtual environment all the information we have available, simulation, sensors, and log files, but augmented with AI, Gen AI, multi-agent systems to actually infer with some probability on the future. And if you infer on the future in a closed-loop system, you can go back now and control. And if I control based on physics, I have better chance to perhaps save something than if I just do a PID or PLC controller. So with this information, we try to synthesize all this into a picture that shows what digital twins can do for manufacturing. The picture on the left is the conceptual org chart of what happens on the diagram on the right. So we collaborate with universities and the government to understand how we can do in-loop correction of a dynamic system that produces troves of data as it makes something and correct that system dynamically without stopping the operation. How can this be done? Well, we think of I'm sorry, can we go back if I can? Yes. We think of digital systems, digital twin systems here, as a synthesis of 2 streams of information, physical information and digital information. Once you combine the 2, you create the basis now to have this big AI and ML box in the middle where you can actually orchestrate a number of functions from which the items in yellow at the bottom can actually happen. Optimization, predictive analytics, maintenance, fault detection, process planning, and of course, model design and manufacturing. And how we implement this on the right? We implement this on systems like the ones you saw earlier by DMG Mori that are able to do 3 functions. First of all, mirror as you built. create a picture of something you're making 100% at 100% of the time you're actually making it. Understand and qualify what you make at any given instance of time t. And of course, if possible, close loop now and correct before something happens to make this performance even better. So with this picture, think what is possible to be made, not just with metals, with any known material. If we can improve the way we actually use matter, raw ingredients, to make anything, the future is absolutely bright. So with this, I would like to close here and thank you for listening to a vision of how digital ecosystems, digital twins, and of course the leading role of simulation can come together through AI to provide a forecasting framework of making virtually anything. Thank you, Patrick.
Thank you, Antonio. Now, this is really a fuse of so many technologies. I have some questions. We have time for questions. I will open with one. You mentioned the synchronicity at the very beginning of the talk between the virtual and the real. And you mentioned mirror. But what is exactly, I would say, the grammar between the virtual and the real with respect to time? Because uncertainty, quantification, multi-fidelity, this, I have the impression, entails a much more profound relationship between the virtual and the real than just synchronization. What do you think?
Very good question, Patrick, and goes to the science of things. We can always trick our eyes to synchronize something virtual with something physical. This can happen in multiple ways. But as Patrick knows very well, in simulation, time is rather a different concept than what physical time might be. What we mean here is a verification, validation, and certain quantification linkage between the two. At time t, the status of a given system can be determined. Think of a heart, right? Think of an organ in a human body. We understand the physiology, we understand the performance. The problem becomes when you have a single or multiple sensor data or simulation data coming at the same time. Can they qualify the same state in a vector formation, like the first speaker said from Google, that actually can be characteristic of what we call state description?
Yep.
The state description now could be an infinite dimension vector, or what we call an information about the status of a given dynamic system. But if I can actually describe with, let's say, principal components, the state of a given system, an organ, a machine, a material, with descriptors that actually could be sensitive enough to understand the nuance of a dynamic system, then the question is, what can I do to actually inform my simulation with this information that will make it not just accurate, but what we call fidelity-wise reliable? If that happens now, and I can trust my simulation environment to produce new data, I can generate, in a generative AI or not way, new information about the system before this information comes to me for the sensors. Essentially predict what the sensors, predict what the simulation will do before it happens. So that VVUQ, verification, validation, certain qualification, is exactly the linkage between connecting IoT, the IT of the world, and OT, with that framework of math that will give us better reliability and better certainty that we can achieve that connection in a very fidelity-wise way.
I have the impression that listening to you, you know, Richard Feynman used to say, what I can't explain, I cannot represent.
Absolutely.
And you're saying what I don't probe, I cannot build.
Absolutely.
Basically.
Exactly.
Are there any questions on the room? Over here, Mike, over here. And then behind.
So I'll give some context here. So when I was doing my PhD, it was in flight in fruit flies. And they do things that seem really amazing, these dynamical systems, but they're mostly hardwired.
Yes.
And there's a lot of passive physical elements and basically hardwired computational elements.
Yes.
And then there's this piece of like, how much does a neural network or computation fit on top? So my question about the system is, in terms of time, like latency and cost,
yes,
how do you fit the LLM in the middle of these dynamic systems?
You heard Dan talking earlier about this new AMD Ryzen Pro chip that has NPUs. Not every architecture of neural networks is built the same. So we are trying to optimize the use of multi-agent or generative AI systems in hardware that can optimize two things: the amount of time it trains a system, or the amount of time to deploy a different AI system on the hardware you're actually using in a form factor that makes sense. In some applications, we can achieve having a high-performance computing environment next to our instrument. But imagine flying a drone or inspecting an insect as it flies around the room here. You cannot really put this form factor on it, right? So the idea is to actually create multiple examples of automated edge intelligence at the form factor that makes sense to run the appropriate model for the type of function you're monitoring. Not every 4 billion parameter neural network model will work for a fruit fly, for instance. Very good example. But if you train that model and you can containerize it in a way to put it in a device that can be as simple as a Raspberry Pi or something more advanced like the Ryzen AMD Pro chip that can work on that particular form factor to be installed in a haptic device or something on the device you're monitoring, then what we can achieve with AI is impressive. So we're talking about the synthesis now between hardware and software into form factors that can be right there where information is produced.
There was a question just here.
Yeah, not so much a question as an observation and a comment. So I'm intrigued by your presentation of both the virtual and the real being in sync, and then having the virtual get out in front of the real.
Exactly.
But the observation of the let's say rhetorical question, this is now mirroring science fiction, because if your virtual detects something that you don't want to have happen, then you are actually going to go back and change the present. So now you have almost an infinite possibility of future.
That's
so
right.
This is a quandary. I don't know how you plan to solve it, but it's something that I find quite intriguing.
As a PhD student, Markovian assumptions were always my nightmare because I had to prove them. But I'll tell you this. Simulation is a compilation of many parameters, but most importantly about assumptions. We make assumptions. Let's call them boundary conditions, initial conditions. Every simulation could be wrong or could be precisely wrong. And I like the second part. What we're trying to do is use the power of simulation computing in an environment where we make real-time adjustments to the assumptions of what the model can produce and make essentially a conjunction of this with something we can label a ground truth. What could be a ground truth? No one said that if I make a part on a Tuesday, I cannot leverage a database of 10,000 parts that I made 10 years now of these data points. But if I use AI now to use the data trend of ground truth, then what I'm doing at time t, I'm comparing what I have from simulation and sensing with what I consider to be ground truth, bounded with VVQ, and try to go backwards now and say, can I predict t-1? And if I can do this, can I keep doing this in a window of time so I can constantly go back and forward, and adjust where I am based on dynamic conditions. Think of an EV, think of a drone. If I can learn as I do in a baseline-less way, then I have a way to dynamically incorporate information that previously simulations didn't have. That's the context of what we're trying to achieve here. And I agree with you that error and uncertainty quantification of that is a big concept that as computing and simulation gets better, I think we're going to get much more accurate and be able to do the t+1 and then extend to t+n steps away from where the state is right now. But excellent point.
And I guess that's also the reason why we use the term virtual twin.
Exactly.
Because virtual is not just a replica, it's the exploration of the many possibilities, like a headlamp, showing you the possible ways. Well, let's thank Antonos Kontsos for this presentation and AI for manufacturing.